with the people connecting online, I can't log into the canvas. This freaking mouse is not moving at all. Well, it's moving now. No, it's not. So anyway, so if you can let them know, I can't start the Zoom today. So I'm going to record my lecture on my own computer, and then we'll upload to my afterwards. So if you got contact with those people, just let them know I can start the Zoom on Canvas. All right. So let's do a very quick review of what we did in the previous lecture. Okay, so it's about surface integrals. Surface integral, in principle, it's about, okay, it's this formula right here. We call this as a flux, right? If you recall that. It gives us a concept of flux, or how much of this quantity represented by this vector field F is going through a certain surface S in unit amount of time. And it's a double integral because you're integrating over a surface. So what we did in the first case is, we look at the first case is, if we have a spherical surface, and this surface is centered around origin. And that's the first case we'll look at it. Under this case, what would this surface integral or the flux calculation look like? Okay. So just to grab maybe another picture from the previous lecture. So as you can see, the key at here is to get an information for n hat and also information for dA. Right? So if you can get information for n hat dA, then we can carry out this double integral at here. For a spherical surface centered around the origin, so the way we did it is we picked a small patch from the surface of the sphere, right? And we look at essentially what is the dA representing this small patch. Because it's a sphere, so the rho, which is the radius, will be in a constant. And you can consider that small patch as rectangle, so you can approximate using an area of a rectangle for the little patch there. And you can end up with dA equal to a squared sine phi d phi d theta. A is the radius of the sphere. And n hat is a unit vector perpendicular to the surface. For a sphere, you pick any point on a sphere, and we have demonstrated that you can always create a vector from origin to that point. And the OP vector is perpendicular to the surface. So OP basically is a reading vector, right? It's a vector pointing out readingly. So OP is perpendicular surface, and you normalize OP, you get a unit vector, and that unit vector basically is this one here. So overall, you get the dA and n hat in this expression, but now it's a mixture of phi angle, theta angle, and x, y, z. And because it's spheres, we wanted to use spherical coordinates. So with the relationship between x, y, z on the surface of the sphere is given by these three expressions. So very similar to the spherical coordinates expression, except that you replace the rho with a constant radius a at here. So that's your xy. So you need to replace the xy for this xy here, right, with the three expressions over here. And don't forget that we're integrating a vector field, right, over this surface. So the vector field F is represented with the three components M and P. So each one of the component needs to be transformed into this spherical coordinates 2, phi and theta. Right? So everything has to be at the end of the expression is all about phi and theta. Right? So that way, you get an overexpression for this surface integral using spherical coordinates when this is a sphere centered on origin. So you get an expression something like that. Okay? Yeah. So that's what we're going to look at it today. Let's look at an example, see how we can calculate if a surface is a sphere. Let's take a look at the following example here. Consider this vector field, F equal to 0, 0, Z. Okay. And S is given by a sphere with a radius of A. And if there's nothing specified, right, this is basically, it's a whole spherical surface. Now sometimes you probably will see an additional condition saying, for example, Z greater than 0. And if that's the case, then you're looking at just half of the spherical surface, right? Okay. So let's calculate using the formulas. What is the flux? Okay. So very straightforward calculation. Number one, calculate. Number one, you should write down the n hat as we just wrote it down. N hat is 1 over A x y z. And the dA, right, this dA equal to A squared sine phi d phi d theta. Okay, so once you have these two wrote it down, then for the F, you can write it F. You can calculate this offline first before you insert it into the surface integral. Okay, so let's calculate what is F dot n hat. F is 0, 0, Z dot this n hat 1 over A x y z. Dot product, multiply each component and then add them together. And so you got 0, 0 here, and that's pretty convenient. You got 1 over 1 over A multiplied by Z squared for this dot product. Okay, so now I'm going to substitute everything into this surface integral formula. Okay, so the dot product is 1 over A Z squared. dA is A squared sine phi d phi d theta. After substituting it, you got a little bit of mixture of Cartesian coordinates and spherical coordinates here. So I need to replace the Z with A cosine phi. So Z, replace it with A cosine phi. Okay. Now simplify. So you do have this A cancel this here, it becomes just 1A, but you have A squared out of this A cosine phi squared. So we end up with A squared, A cubed, and then cosine phi squared sine phi d theta. Okay, so still the same surface, we're integrating. It's the whole spherical surface. Okay, so last step, right, is to do the integral. And the integral only involves two variables, the phi and the theta, which are part of the spherical coordinates. Right? So the limits, the integral, so next step, when you do the integral, when you try to find the integral limits for phi and theta, you're going to follow exactly the same procedure as you have done for triple integrals using spherical coordinates. So if you recall, how do I find limits for phi? when we do triple integral using spherical coordinates, right? So now you're not bothered with this rho anymore, right? You only worry about the phi angle. So this is the whole sphere that we're looking at here. A typical procedure to find the integral limits for spherical coordinates is that you draw a reading line out of it. Okay? And the first step is to find the rho, but of course now you don't have to worry about the rho anymore. But the second step is to look for the phi limits. And phi is the angle between z-axis and the line that you had just drawn. So starting from z-axis and rotate right, all the way down to the bottom negative z-axis. Okay. For phi angle, the maximum value is pi. You cannot exceed pi. And minimum is 0. So for this case, because it's whole surface, so certainly your phi limits will start from 0 and end up at pi. Right. So start here and at pi because that's the whole surface you're looking at. So your limit for phi, then you can insert here as 0 to pi. And then finally, theta angle. Right. Theta angle is determined by the shadow of the surface inside xy plane. The shadow is this circle at here, and you draw a reading line out of the circle, and then you rotate around this whole circle, see where the whole circles are, where the edges sandwich in the circle. So in this case, 0 to 2 pi, right, for the theta. So exactly the same procedure as you have done to find limits for triple integral in spherical coordinates. Okay, so finally, you can calculate this triple integral, this double integral. Right? So when you calculate the double integral, the first step is d phi, and for this question, I missed a square here. So simple substitution technique should be enough for this question. Okay. So let me write down one more step here, just in case you couldn't see that. So keep cosine phi squared. So the sine phi d phi can be written down as d cosine phi, and you put a negative in the front, and then d theta. So d cosine phi give you back a negative sine phi d phi. So negative cancel, and you get back sine phi d phi. So now you have the same cosine phi as the integrand, as the dummy variable, and then you can integrate, substitute the limits. There's nothing to do with the theta, so theta will just 2 pi. So you can calculate this carefully. You get 3 over 4 pi a cubed. Happen to be actually the volume, right, of this sphere. It's just coincidence. Right. So this is the procedure of how to conduct surface integral using a spherical coordinates, but not all of the spherical coordinates, only the partial, right, phi and the theta. Okay. Now, another thing I think I should probably be clear a little bit is I should say outward flux, okay, for the question. Calculate the outward flux. The reason is, if I don't say it's outward flux, so technically your n hat has 2 directions, right? One pointing out, one pointing inward. Because it's outward flux, so the n hat, we pick the positive at here instead of the negative. So that's the key word sometimes you need to watch out for the question. Are you looking for the inward flux or outward flux? Okay, is that good? So if you look at this question, right, the way how it's solved, of course, you can force yourself to memorize a couple of formula, but you don't really have to, right? If you know the triple integral formula, you can naturally actually get this formula for the surface integral. But then in the end, when you do the calculation, because there's really nothing new at here, right? So the limits for phi and theta is exactly what we have learned. So this double integral right here, it's really not anything new, right? Even though the formula is a new formula, but the computation involved, right, subsequently, there's nothing new over there. Okay, so that's a surface. When you have a surface, a spherical surface centered around the origin. Okay, that's also important. It's centered around the origin. If it's a sphere not centered around the origin, then what we have demonstrated here actually doesn't work. All right, yeah. So you have to shift it to the origin first, and then you do it. Okay. Shift means change of variables. All right, so let's look at the second special case called planar surface. Planar surface means, for example, you have a surface parallel to the xy plane, and we just call it z equal to a. Right, that's a plane. It's parallel to xy plane, and it's a planar surface. And you could have a different parallel surface, maybe parallel to the xz or yz. We'll see that after we derive the results here. And also the same thing. So let's see, we got a certain vector field in presence within the 3D space represented by M and P components. So the question is exactly the same process. Here is your surface integral formula. Okay. Then given this kind of special surface, what is n hat? What is dA? Okay. And then we can see how do I find this double integral based on the information for n hat and dA. Okay. So let's tackle the easy one. Right? N hat. N hats represent a unit vector perpendicular to this surface. If this is a surface right now in the drawing, so what do you think n hat should be? Well, sorry, what hat? K hat, exactly, right? But you do have two directions, so technically you should say positive, negative k hat. Excellent. Right? So you can just draw n hat here. Of course, that's n hat, that's k hat, and down is negative k hat. So n hat equal to positive, negative k hat. That's easy. Or you can write it as a positive, negative 0, 0, 1. All right, so next is dA. Right, dA in principle is a very small patch of area on the surface S. So if I'm going to take a very small patch of area on the surface of S, then this is parallel with the xy plane. So technically, right, one side can be delta x, the other side can be delta y. Then dA, right? If I talk it not delta a, if I talk about dA, then it's basically dx dy. Right? Exactly similar to what we have done for a double integral over a certain region R. So now you got both of these, okay, and then we're ready to plug it into the surface integral. So surface integral in this case is M and P dot this n hat. Okay. I'm going to use just a positive one to illustrate. So if I just use a positive one, it's 0, 0, 1, meaning I'm calculating flux, upward flux, right? So in the positive z-axis direction. Now this dot product give you just P times 1, okay, and the rest of the 0. Okay, so P has originally, right? So for original M and P, all of them are a function of x, y, z. Okay, so originally all three of them are a function of x, y, z. Now I'm going to leave this as question mark here, okay? And then we'll come back to this, okay? And then dx, dy. Okay? Okay? And s. Now, if I don't leave a question mark, if I just write a z here, right? If I just write a z, then there's something wrong, because my integral is about x and y, and then you got a z added here. That you're not going to get anywhere, right? You're not going to get the final result as a number. So this is where you have to go back to your surface. What is a surface? The surface is z equal to a. So surface is exactly at the z equal to a. So that's why the z over here, you have to replace that with the actual surface location, z equal to a. And now you have everything in terms of x and y, which basically you can calculate as a double integral. And the x and y limits, okay, these x and y limits, and they are determined by the shadow of the s in xy plane. I mean, technically, the shadow will be exactly the same geometry as the plane you sketch here, because you look down. If you look from top view, and you see exactly the same patch, right? Same surface. Right? If it's a rectangle, then you got a rectangle. If your surface is a circle hovering somewhere at the z equal to 3 or 4, right? Then the shadow is a circle. Okay. So it's all determined by the geometry of this planar surface. So it depends on how it's given by the question. Okay. So let's take a look at. Actually, don't need just before we take a look at an example, maybe really an example. But anyway, so let's take a look at a different planar surface. Okay, so this is the planar surface when z equal to a. So how about a different surface? Let's say x equal to b. Right. So then, if I have to draw it, x equal to b means you have a plane, a planar patch. If this is b here, right, it's passing through intersect this x-axis at b, and parallel to the z and y axis. Right, that's the planar surface representing x equal to b. Same thing. So then you can try to find n hat first, okay, for this surface. So what would be the n hat if you have a plane like this, parallel to the zy plane? Sorry? I hat. Again, positive and negative. Don't forget you've got two directions. So depending on the question, are you looking for the flux in the positive x direction or in the negative x direction? Okay. And then dA, okay, you're using, instead of xy now, this is in the zy, so d doesn't matter, dz, dy, or dy, dz, they're all okay. Right, so it's just the order of integration difference. Right, that's when you have a plane parallel to the zy. And lastly, when you have another one, which is, let's say, called y equal to c. If c is over here, then you got a plane parallel to the xz. And then n hats, right, will be negative, positive, negative g hat. dA is going to be dx, dz. Okay, so that's the three different, basically, surfaces, right? Simple surface. Both of them are parallel to somewhere. So then you can calculate accordingly. So let's take a look at quickly local example. Giving a constant vector field. So this is a constant vector field, F. And the surface S is given as Z equal to 0. Well, let's even just put a Z equal to 1 here. And X is between 0 and 2. Y is between 0 and 3. So find the flux of this vector field in the k-hat direction. Okay. First step, sketch this surface. It gives you a z equal to 1. So z equal to 1. And then x ranging from 0 to 2, y ranging from 0 to 3. So x 0 to 2, y to 3. Okay. I mean, technically, if you have to draw this in the xy plane, right? So you got basically a rectangle in the xy plane by looking at these two conditions. But now you also have a z equal to 1. Basically means what you're actually looking at is a surface, okay, hovering on top of xy plane. Okay. Right, this is z equal to 1. So that's the actual surface z. Okay. So now I'm ready to use the formulas that we have just derived. So we're looking at it's a plane parallel to xy, then it's also asking for a flux in the k-hat direction. So n hat should be k-hat, so 0, 0, 1. And then dA is going to be dx dy. And dx dy, the limits will be determined by the shadow, which is this rectangle. And that's very simple. We're going to show that. And now I'm going to put everything together. F is negative 1, 2, 3, dot, n hat 0, 0, 1, and dA dx dy. Okay. Yeah. So if I change the question slightly, okay, let's say if I change the question instead of a 3 at here, so let's just suppose I put this z square. So then what do you think I should replace the z with? Exactly. Okay, so don't forget the information of z given by the surface. So z should be 1 in this case. You replace that. All right. So let's use this one to do the calculation. So negative 1, 2, 1 dot 0, 0, 1 dx dy. That gives me still a constant value, so you end up with just 1, right? And dx dy. Okay. So you don't have to actually, if you are quick enough from here, you don't really have to do anything at all. You can immediately get the results. This one simply gives you what? The area of this surface S, which is rectangle. So the area of this is 2 times 3 equal to 6. Okay? And of course, this is only true because you got a 1 in here, otherwise it wouldn't be the area, right? So this is the idea when you have a simple surface that's parallel to any one of the side planes, xy or xz or yz. And you can calculate simply as a double integral by picking 2 variables carefully. Okay. That's case number 2. Another special case when the surface is parallel to one of the plane. Okay. And third case is a cylindrical surface with radius of A and centered around z-axis. Okay, that's the third case. If you got a cylinder, okay, so I'm going to draw an arbitrary cylinder right here. The cylinder is centered around the z-axis, right? And it has a radius of a. The cylinder, if it doesn't specify, it could go way above the xy plane, or could also go down below the xy plane. This drawing here is like that. Okay. Now we are calculating, for example, let's say what is a surface, what is the flux, okay, over that cylindrical surface. Again, it could be a flux going outward, or it could be a flux going inward. Right? So if I pick a surface, pick a point on the surface, then you can have a unit vector pointing outward or unit vector pointing inward. So n hat could be this way or could be the other way. Okay, so I'm just going to draw a few n hat pointing outwards here. All right, so first question. Let's take a look at what is n hat. What will be a candidate for the n hat? Because it is a special one, right? So before we get to the n hat here, so let me ask you a question, maybe a simple question here. Let's say if I give you a circle, and this circle has a radius of a. Basically, it's this circle. When you look it down, okay, look from the top for the cylinder. And then if I ask you, if I pick a point on the edge of the circle, can you create an n hat, or can you give a candidate for this n hat that's perpendicular to this circle or to the curve right on the edge of this circle? So what would be an n hat? So you pick a point. Let's say this point has a coordinates x, y. So what could be a candidate that's perpendicular? Yes. I use x, y. Let's just use x, y for now. No vector. I'm looking for a vector perpendicular to the circle, right? Not a distance. If this is a point P, if I connect this origin to point P, does the vector OP perpendicular to the circle, right? It's similar to the spherical surface, isn't it? Right. So you draw a radiant vector. It's perpendicular to that spherical surface. Now you connect this. It's perpendicular to the circular curve. Okay. So OP is perpendicular to that. And what is OP vector? XY, right? And what is n hat? Just normalize it. So you got xy divided by its magnitude. And what's the OP's magnitude? A, exactly. So your n hat for a circle is 1 over a times xy. Now back to the cylinder, right? Back to the cylinder. What I just solved is to find a vector pointing perpendicular to the bottom edge. But if I pick a point right here, okay, if I pick a point right here, suppose that this point is at a height of a z. So what do you think the n hat would be? This n hat. Compared to the n hat created at this location, which has a z equal to 0. They're both parallel, right? They're both parallel. And the only difference is this is z equal to 0, this at z. But the xy component should be exactly the same. So the n hat, in this case, is 1 over a x, y, and then, what should I put it for the z component? What should I put it? So for this n hat here and compared to this n hat here, they're parallel. The only difference is this is at the Z location. But I'm creating a 3D vector, right? Representing any locations. So what do you think I should put it over here? 0, exactly, right? It doesn't really matter where you place your n hat, because when you look down from the top, this and this exactly the same. Okay? So this is your n hat for a cylindrical surface. It's a univector, perpendicular to it. Of course, this is pointing outward, and you can certainly put a positive and negative in front of it, right, to give you 2 directions. Okay? Yeah. So let's just put a positive and negative here. Okay? Good. So now once we solve the n hat, and the next question is dA. Okay? So for dA, and dA referring to a small patch on the cylindrical surface. I'm going to borrow one of my pictures from the lecture notes. Okay. So this is in the lecture notes how we can create a small patch on the cylindrical surface. As you can clearly see, it's created by rotating the delta theta a little bit, and also change in the z direction, a small delta z, delta theta. Right? So then you can create a very small patch on the cylindrical surface. And remember, this on the cylindrical surface basically means that a value is not a variable, right? It's constant, and that's the radius of the cylinder. Okay? Then if we consider this as very small, then we consider this as a rectangle. Then the area of this rectangle, which is dA, can be just a multiplication of one side multiplied by the other side. So one side, which is this, that's delta z. And the other side, which is this one, that's A multiplied by delta theta. So one side multiplied by the other side, you get the small rectangular area. Right, so that's your dA, but of course I should use a d at here, right, because I use a d over here. Right. So dA equal to, simplify it, A times dz d theta. A times dz d theta. And if you recall the formula for cylindrical coordinates for triple integral, and that's rho, and r times dz dr d theta. Right, if you recall that. Now the r becomes a because you're working on the surface. It's constant radius. So you're not really worried about this changing r, right, in the r direction. That's why you don't have this. This has become a. Right. This is a simplified version of cylindrical coordinates, okay, and when you're working with a triple integral. Okay. So now you got n hat, you got dA, okay, and again they're in a relatively mixed format here, so I need to basically put everything into consistently cylindrical coordinates. Okay, cylindrical coordinates originally is r theta z, but of course r is constant, so now we're only worried about is theta and z, okay, in this case. So you already got a z theta here. What's not consistent is this x, y, right, in the n hat. So your x, okay, if you recall the formula for cylindrical coordinates, a times cosine theta, right, instead of r, you have a here, and y equal to a times sine theta, okay, and z is still z. Okay. That's a connection between your Cartesian and the current cylindrical surface. Okay. So you need to replace all the x, y, z with these three expressions. So I think I'm ready to derive a generic formula now. F dot n hat dA, and F has three components, m and p, and n hat is 1 over a x, y, 0, and dA is derived as a times dz d theta. The dot product gives you 1 over a, well, this 1 over a cancel with this a. So you end up with just m times x plus n times y, dz d theta. Okay. So for all the x, y, and m, n, right? So m probably is a function of x, y, z. You got to replace the x with a times cosine theta, y with a sine theta, okay, and z, you keep it as z, that's okay. And same thing for the function n. You have to replace the x and y with the corresponding expression a cosine, a sine, and keep the z as it is. The x, y over there, of course, you still have to replace with a cosine, a sine. And the last step is to find limits for z and theta, as you have done for a cylindrical surface, a cylindrical triple integral. Okay? Find the limits for z and theta. So I'm going to demonstrate that through an example. Okay? All right. So let's take a look at the example here. F equal to x, z, negative y. S is a cylinder, x squared plus y squared equal to 1. And z is between 0 and 1. So this is your cylindrical surface. And let's calculate outward flux. Okay. Outward flux. Whenever it says outward flux, so that basically is a hint at what choice of n hat that you should choose, right? Yeah. So if you have to sketch this cylindrical surface, because it says x squared plus y squared to 1, so you have a circle, unit circle, right? And z is between 0 and 1, so basically it's a very precise drawing, but it's a cylinder sitting on the xy plane with the top at z equal to 1. Okay, so we're looking for a flux outward of this cylindrical surface here. First step, let's write down n hat. Okay. Basically, your radius here, a is 1, so you're 1 over 1, and then x, y, 0. And dA is technically, what is dA again? It's a times dz d theta. So again, a is 1, so your a is just dz d theta. Then ready to plug in everything for the surface integral or the flux calculation. Vector field is x, z, negative y. And dot n hat x, y, 0. dA is dz d theta. The dot product gives us x squared minus yz plus yz, and then dz d theta. Okay, so right now it's a mixture of the Cartesian and the z. And then we need to replace the x, y, z with three expressions. But technically, you don't touch the z, because z is still capital Z. But you just replace the x with a cosine theta and y with a sine theta. A is 1, so x is cosine theta, and y is sine theta times z. dz d theta. Right, so this is a setup. And the last step is to figure out the limits for the z and the theta. In the order, okay, so typically will be dz d theta first. So this is where you need to recall how do you find the limits for z and theta when you're dealing with a triple integral using cylindrical coordinates. Okay? If you recall that for z limits, you find the shadow of this cylindrical surface, and then you draw arrow lines in the z-axis direction. So your z min is the first contact, z max is the second contact, and this one is pretty straightforward. It's 0 to 1, and that's your z limit. And theta limit is determined by the shadow of the surface in the xy plane, which is the circle, unit circle here, and you can just draw a reading line and rotate the reading line, okay, around this shadow. In this case, a whole shadow. So your theta got to be 0 to 2 pi. So you got all the limits, and this is not a very difficult calculation because literally you're just calculating cosine theta squared and sine theta z. Okay? Now, maybe a little bit of difficulty in calculating the integrals of cosine theta squared. There's a trig identity, basically. Cosine 2 theta minus 1 divided by 2 is cosine theta squared, so you can use that trig identity to calculate this. Okay, so take a look at the lecture notes. It should be okay to get a pi for this calculation of flux. Right. Again, right, it's a flux, it's a new concept, but when it is down to the fundamental calculations at here, right, there's no difference from a double integral. Okay? There's no difference from what you have done. It's a simplified triple integral, basically, right, using cylindrical coordinates. Okay. So before we finish, so let me ask a different question. Okay, same question here, right? Same question. So this is sometimes it's a little bit tricky. You have to watch this carefully here. Okay. Now, if I change this question, okay, if the question changed to you have a surface. Okay, and the surface consists of this cylindrical surface. It consists of cylindrical. This basically the current question, and then also says including the top and the bottom. Okay. So basically, we're making it a closed surface. Right. The previous one is just a cylindrical surface; it's not closed. So now we're closing it with the top and bottom surface. Okay? And then we said, and the question would ask is, so then what will be the outward flux? Okay. Same question, how we calculate outward flux. So this is somewhere when you see this kind of question, right? So you got to identify what kind of a surface you're dealing with. Okay? If this is a surface consists of 3 pieces, then basically you have S equal to S1 plus S2 plus S3. So you have 3 different surfaces here, right? The side, let's call this S1, and then top S2, and then bottom, let's call it S3. Then outward flux means you have to use the total surface to calculate this outward flux. And it's equivalent to calculate the surface integral for each one of the surfaces. And this one we just done it, right? The question basically, what about these two, S2 and S3? One is the bottom and the other one is the top. And then you have to identify what kind of surface is S2, both S2 and S3 are exactly what case is it? Case 2, right? Exactly case. They are both parallel to the xy plane. So you need to use the case 2 formula to calculate this surface integral of this. And when you come to the case 2, examine it, you have to identify n hat. So tell me what would be the choice of n hat for S2? S2 is the top one. K hat, excellent, because you choose K hat because it's outward, right? So what about S3? Excellent. That's exactly my point here. It's outward, the bottom surface outward is this way. Right. So when you see a surface, when you once you identify the surface, and the next step when you identify the end head, you have to look at what kind of direction of a flux is required to calculate. And if you can have done this, and the rest of it are fairly straightforward. Both a circle, and you can integrate over that circle to get this double integral. So you can try it to get to what will be the results if this is a new question. All right, I'll just stop here. We got just one last case, number 4, to go through, which is a generic case, more generic case than the first 3. And then we can talk about the new topics. By the way, we got the last quiz lining up for this weekend, which will be on the, what is it on again? Actually, I need to look at it. So, similar format as quiz 4. Okay. Yep, interesting.